Assalamualaikum to Puan Saleha, and my name is Muhammad Fidaus, and today I will present for Simulation Lab 4 Introduction to AC Fundamental with RL and RC Circuit. So for my part, I will be explaining the function of function generator. Function generator is a piece of electronic test instrument used to generate and deliver standard waveform, typically sine and square wave, to a device under test. It can be used to test a design or confirm that a piece of electronic equipment is working as intended. In addition, there are many different types of signal generator with different purpose and application and at varying level of expense. These types include function generator, RF and micro signal generator, pitch generator, arbitrary waveform generator, digital pattern generator, and frequency generator. This is the example of function generator. Then LSG15 signal generator and analog RF signal generator.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal, and now this is my part. So for oscilloscope, function of oscilloscope is to capture voltage per division in a circuit. Okay, and we can determine voltage per division in a circuit using the graph of oscilloscope, and we also can determine the unwanted signal. The definition of signal is voltage per division. So that is the signal. So in oscilloscope, we can capture signal of the circuit. All right. Okay. 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 There is two types of oscilloscope. That is analog and also digital. Okay. Let me tell you about uh, the function of oscilloscope using part A. Using part A, which is measure the frequency of sinusoidal waveform signal. Don't forget to calibrate your oscilloscope. Set the signal generator and oscilloscope as stable 1. How to calibrate your oscilloscope? The calibration goes like this. Positive terminal of oscilloscope goes to positive function generator. Negative go to COM. And for the channel B, positive go to COM and negative go to positive. Why we do like that? Because we want the signal to inversely from we want the channel B and channel A will be more clear and easy to read. So if we put positive to positive and negative to COM of channel B, so the signal will be under the signal of channel A. We want to do like this. We have to put positive to COM and negative to positive function generator of channel B. Alright. Okay, after that we have already calibrate our oscilloscope. And what to do? Set the signal generator and oscilloscope as stable 1. Signal generator. Oh, we doesn't use signal generator, but we use function generator. And we can look at here. We have set the frequency to 2 kHz and amplitude to 3 Vp. And after that, we also have connected the function generator to channel 1 and also channel 2 and press auto set. This setting is for the it's not for the offline, it's not for the in computer apps, but it's the auto set. You must have a real things to set the auto set. And for each setting of the signal generator in table 2, zoom in, okay. And for 2 kilohertz frequency, okay. look at, I just want to give an example of two frequency, and the other setting I just give the data. And for two frequency, as we can look here, this is 2 kilohertz and 3 VP. So this is the graph. This is the graph where we can find, we for channel B I have already changed the color to change the color of the probe of channel B to blue, so we can easily identify which one is channel A and which one is channel B. For this one, the channel B is blue one, so we put it for channel B, we put it 0. And okay, what is the question? We see the question is horizontal setting, distance, and periods. Okay, for horizontal setting for 2 kilohertz frequency is 100 microsecond. This one can be changed. Time base is for horizontal, and channel A, channel B is for vertical. So if we change the time base, it will become much more shorter. So we have to put it, and we have to set the time base to become more easily to read and more easily to plot on the graph after this. Okay, for a horizontal setting is 100 microsecond, and the distance, so the distance is in 1 period. So look at this, here until here is 1 period. So how many box or how many division in the period? So we calculate 1 2 3 4 5, a little bit here, little bit here, so the division or the distance will become 5 division. So 100, okay, as you can see here, 100 is our horizontal setting, and 5 division or distance is 5. So the period 100 multiplied by 5, it will become 500 microsecond. 500 microsecond. All right. We also can calculate the VP or the VPP of of the the circuit by referring to this horizontal setting. No, vertical setting. Horizontal setting is for us to find period, and for vertical setting is for us to find VP and also VPP. As you can see here, the horizontal setting for channel A, this one is channel A, is 1 volt per division. So 1 box or 1 division equal to 1. So for VP, I give you an example for VP, right? For VP is from center to peak. All right. So for VP is we can calculate the VP is 1 2 3. So 3 multiplied by 1, so the VP will become 3 volt. And so for the VPP, it has 1 2 3 4 5 6. The distance of vertical distance is 6, and the vertical setting is 1. So 1 multiplied by 6 will become 6 VPP. All right. Okay. For the 10 kilohertz, the horizontal setting is 20. The distance is 5, as you can see here. Let me show you the graph. The horizontal setting is 5. So that, look at this. This is graph for 10 kilohertz, and this is graph for 50 kilohertz. So for 10 kilohertz frequency, the horizontal setting is 20 microsecond per division, and resistance is 5 division, so the period is 100 microsecond. And for 50 kilohertz frequency, the horizontal setting is 5 microsecond per division, and the resistance is 4 division, and 5 multiplied by 4 is 20 microsecond. That's all from my part. Thank you.
So for part B, measuring the phase angle difference. First, calculate the phase angle difference for each capacitor value in table 4 using equation 5. Record them in table 4. This is the table 3. Set the signal generator and oscilloscope as table 3. So we set the circuit just like this. Set the signal generator to frequency hertz 2k, then your oscilloscope, coupling AC, time base auto set, vertical amplitude auto set. So both channel set to AC. Then assemble the circuit of figure 8 using your signal generator output as your input source for your circuit of figure 8. So this is the table 3, figure 8 circuit. So the connect channel 1 of the oscilloscope to the input voltage Vs. This is the channel 1, channel AB. The positive go to the positive of capacitor, and then negative goes to the ground. For channel 2 of the oscilloscope to the input output voltage Vr. So this is channel 2. Channel B, positive goes to the here output capacitor, and then this one goes to the ground. Adjust the setting of signal generator to get the sinusoidal form with 6 VPP. So we set the function generator amplitude to 3 because the VPP is 6. Then measure the phase angle between Vs and Vr. Compare the result with the calculation. Sketch both waveform. Okay, first we do the calculation. The calculation for capacitance will be like this. First, we find the XC. XC is equal to 1 over 2 pi FC. Then we get here is 1 over 2 pi 2k frequency, and 0 times 0.33 microfarad, and then the answer is 241.14 ohm. And then we find the phase angle. Phase angle is tan inverse times XC over R. Then tan inverse, we take the XC here, 241.14 over 33 ohm, and then the answer is 82.21 degree. Same situation for 1 microfarad and 10 microfarad. So we go back to the table. Then we do the measurement. First, for the measurement, show the measurement calculation first. This is the measurement, 0.33 microfarad. The phase angle for to find measurement is equal y, phase angle equal y over d times 360 degree. So to find y and d, we go to the multisim. We do the 0.33 microfarad, set the capacitor to 0.33 microfarad. Then run. Open the oscilloscope. We set the time base scale. Find one that can read. easily to read, and then set the channel A scale just like 6 VPP. So this is 6 VPP, and then channel B 200 MV. So to calculate the D period, one cycle, go to the, so this is one cycle. We count the square here, 1 2 3 4 5, this one plus here, and then it will be 5 square, and then times scale 100 microsecond per division, so it will be 500 microsecond per division. This is the period. And then y is different between two signal. So to find different between two signal, the accurate one is, first we select a trace for channel B, then set the cursor 1, set y value to 0, and then select a trace again to channel A AC, and select the cursor 2, set y value to 0. So this is the, wait, first. So these are the accurate one to find the T2 minus T1. This is Y signal difference between two signal, 114.131 microsecond. So we go to the calculation back. So this is Y on the multisystem again, and then we times it with 360 degree. So we get here is 82.17 degree. This is the phase angle in measurement. And then we do the same part for inductance. So for lead and lag, for capacitance here, the lead and lag, sine wave for sine wave in output is output lead by lead the input waveform by 82.70 degree. So it will be the same situation for the other. And then let's do the inductance one, table 5. So for table 5, we add the R winding here, winding resistance, same circuit, only plus the ROW and inductance, and replace the capacitance with inductance. So first we replace stop first. And then series it the R winding with the resistor. And the circuit will be like this for table 5. So we do the 3 millihenry. Okay, here. Then we do the same step for as the capacitance. We set the frequency to 2k Hz, and then amplitude 3 Vp, then set the AC for both channel A and B, and then we run first. Play with the scale for channel A and Y. Okay, pause it, and then be like this. So for inductance, select a trace for channel A, and then the cursor will be cursor 1, not cursor 2, and then set the Y value to 0. Then select a trace for channel B, AC, then set the Y value again to 0. So we get here the Y is the difference between two signal is 63.264 microsecond, T2 minus T1, and then the D period, 1 cycle, 1 box, 2, 3, 4, 5, same box, plus here is 5 box, and then times it with the scale 100 microsecond per division, 500, the equal is 500 microsecond per division. Then go to the calculation for the go to the calculation first, inductance. This is the calculation. Here is XL equal to 2 pi FL. So 2 pi times 2k hertz, then times with 3 millihertz, 3 millihenry, and then we get here is 37.7 ohm. Then we find the phase angle equal to tan inverse times XL over R, resistor plus winding resistance, and then tan inverse times 37.7 over 33 plus 2.2 ohm. Then we get here is 46.96 degree. Then we do the same for 6 millihenry and 10 millihenry. The calculation, we do the measurement. Here is the measurement for table 5. The phase angle equal to Y over D times 360, same as the capacitance. So in Multisim, we get 65.348 micro over 500 micro, then times it with 360, then we get here 47.05. Wait, there's a error. First we must set the R winding according to table. It's not the right RW. So the RW is 2.2. We run it again, then select trace channel A, set Y value to 0, then select trace for channel B, AC, then set Y value for cursor 2, value to 0. Okay. Wrong again. Channel B, AC, set Y value to 0. Okay, and then select trace channel AAC, set Y value to 0. Okay, we get the same value for Y in the measurement here. Yeah. this is the correct one. So the face angle is 47.05 degree. Then we do the same for 6 millihenry and 10 millihenry. So that is all from me. Thank you.